Hi, welcome to Lesson 15a, Simple Rules of Differentiation. The goal of today's lesson is to learn the basic rules of differentiation to determine derivatives of polynomial functions. So the last lesson we had, we looked at finding the derivatives from first principles, which was also, the other way of looking at that is the limit definition of the derivative, and we saw the long way of how to find the derivative of a function. Well, after doing a few of those the long way, hopefully we would have picked up the pattern to see exactly what was kind of happening with the original function as it became then as we took the derivative of that original function, found the gradient function of that original function. So a couple things that we probably noticed was that if your function f of x is x to the power n, then the derivative function f prime of x, that would be n x to the n minus 1. Okay, so this is called the power rule of finding derivatives. If f of x is a constant, and I'll be showing this in a second, then f prime of x is going to be 0. So remember that a constant, this is just like y equals some value, like y equals -3 or -5 or +7 or something like that. And that's going to be a horizontal line, and the gradient, or f prime of x, of a horizontal line is going to be 0 because there's no rise over the length of the line. Therefore, there's no gradient to it, or no slope, and therefore the gradient would equal 0. Another thing that we saw, or I guess we will begin to see more, is that if we have some constant multiplied by the polynomial function, then f prime of x is nothing more than c multiplied by n, x to the n minus 1. So again, we just use this power law. We bring the exponent down in front and subtract 1 from the exponent, and then whatever comes down in front multiplies with that constant that was in front in the first place. And then another thing that we're going to be looking at is if we have the function that's a sum or a difference of two functions or two other terms, then the derivative is nothing more than the sum or difference of the derivatives of each of those. Okay, and we'll see that momentarily. Okay, so proofs are always kind of handy to see in order to kind of get the whole grasp of things. So let's say I'll do this the constant first. So suppose our function is some constant c. Well, we know the limit definition of the derivative is f prime of x equals the limit of f of x plus h minus f of x all over x plus h minus x as h approaches 0. So here's the y2 minus y1 over x2 minus x1. In the denominator, that simplifies down to just h, which is fine. I'll take care of that in the next step. And generally when we have our function, we would replace, in the first function, we would replace x with x plus h. Because remember, we're looking at a function that has some sort of point that we're interested in, x f of x, and then we've got this other point that is some horizontal distance h away from that point. So therefore the coordinates would be x plus h, f of x plus h. So that's where we get the x plus h, and the f of x plus h is that second point that we're looking at. So, and of course we're trying to get these 2 points as close together as possible. So that's why we're taking the limit where h approaches 0, so that this horizontal distance between the 2 points gets closer and closer to 0, thus simulating it only being 1 point, or being so close together that it's effectively 1 point. Okay, so the f of x plus h, well, in this case, this is just a constant. So there's no place to substitute the x plus h into the function in the first place. So f of x plus h is just c anyways. Okay, so then if we just continue on with this process, we have the limit of f of x plus h minus f of x. Well, f of x plus h is c. Too strong here. Minus c, which is the f of x, all over, well, x minus x is 0, and we're just left with the h. Jeez, sorry about that. And then we finally have the limit as h approaches 0 of c, well, c minus c, that's just 0, over h. And remember that this h, the limit as h approaches 0, this denominator never gets to 0, but it gets very, very close to 0. So it gets so small that we get a very, very small value. Now, if I take this case where h is to the right, or the second point is to the right of this point, then that means h is positive. If I were approaching from this other side over here, then in this case, h is going to be less than 0. And over here, h is greater than 0. So either way, we've got a very, very small number here. Very, very small, that's my short form, small positive value, or it could be small negative, but either way, if you're dividing 0 by anything, you just get 0. So therefore, if f of x is a constant, then f prime of x is going to be 0. So if I have and I'll just draw a very quick sketch here. If I have some graph, let's say this is 3, so f of x equals 3, you can plainly see that there is no slope to that, there's no gradient. Well, there is a gradient, but the gradient is 0. Slope meaning that there's like no inclination to it. So the gradient is actually 0, because if we're to look at gradient as delta y, or the y step over delta x, there is no change in y anywhere along here, so the delta y is 0 over all of this delta x, whatever it may be. It could be 1 or it could be 1,000, it doesn't really matter. There's some sort of value down here, and 0 divided by anything is just 0 anyways. So by looking at a constant function, we see that the function itself is just a horizontal line, which gives us the gradient of 0. And that's proven here by using the limit definition of the derivative to find that as well. Okay, so let's move along now to if suppose we have a constant, suppose f of x is some sort of value where we've got some constant multiplied by x to the power n, or actually let's say maybe we'll just say this is u of x just for fun. And so then f prime of x, of course, is going to be the limit of f of x plus h minus f of x all over, well, it's x plus h minus x, but that just simplifies to h anyway, so I'll just leave it as h approaches 0. So I'm going to substitute x plus h in for x here in the beginning. So I've got the limit as h approaches 0 of c times u x plus h minus u of x all over h. Oh, sorry, and this is c u of x, of course, here. And so I see I've got a constant that's common between these two terms. So I can factor that out. So I can factor it out to the front. So I've got c multiplied by u of x plus h minus u of x all over h. And, well, as we know, the limit doesn't affect the constant at all from the first proof I just showed. So let's just kick this out to the front just to get it out of the way. So this limit definition of the derivative ends up being c times the limit of u of x plus h minus u of x all over h as h approaches 0. And, well, this is just the basic definition of the derivative. So then this just becomes c multiplied by u prime of x. And so then we have now proven that if f of x is some function u of x multiplied by a constant, then f prime of x is nothing more than the constant multiplied by u prime of x. So you take the derivative as normal and then just multiply it by the constant. And the last thing I'd like to show you is if f of x is, say, two functions, u of x plus v of x, for example, and then f prime of x. So this is the sum of two. It could even be the subtraction. Let's actually do the subtraction just for variety's sake. So it's the subtraction of two functions. And so this is the limit of u of x plus h minus v of x plus h minus u of x minus v of x all over h, and of course put big brackets around this as well. And so then what we can do is we can kind of tidy things up along the way here. So u of x plus h, and I'll bring this minus u of x to join there, u of x, and then I'll have minus v of x plus h, and I've got a minus negative here, so it's plus v of x all over h, and that's all as h approaches 0, of course, still. And so then what I can do is I can split up these things into two limits. So I'll say the limit as h approaches 0 of u of x plus h minus u of x all over h. And then I'll factor out this minus sign as well. So I'll say minus the limit as h approaches 0 of v of x plus h minus v of x all over h. So when I factor out this negative sign from here, this becomes a subtraction back again like we had in the original function, or in the original form of this first principles. And then when we get this, we just see that these two things are now just the basic form of the derivative. So this is then u prime of x, and then the minus, and then this is just v prime of x. So if f of x equals u of x minus v of x, then f prime of x is u prime of x minus v prime of x. Okay, so those are three proofs to show you, or three proofs using the first principles, or the limit definition of the derivative, to show you how some of these differentiation rules actually work. Okay, so a real basic example. We're going to look at some examples tomorrow, but just a little basic example. So if I said f of x equals, well, a constant, let's say it's negative 1/2. Well, that's a constant, so f prime of x is going to equal 0. If I had f of x equal to x to the power 5, then f prime of x. Well, we're going to bring this 5 down in front, and then subtract 1 from the exponent, so it'll be f of 5x to the power 4. I'm going to change this around a little bit. I'm going to say y equals, let's say this is now 2x to the power 8. Then dy by dx, this is Leibniz notation, dy by dx. Well, this 8 comes down in front and multiplies by that 2, so it's going to be 2 times 8x. And now we subtract 1 from the 8, so you have 7. And then simplifying, that gives us 16x to the power 7. Okay, so we're going to look at a few more tomorrow, but these are just some basic examples to kind of help whet your hunger, or whet your appetite for differentiation. And so what I'd like you to do before we go is I'd like you to take a look at examples 1 and 2 on page 362, and ask the self-tutor to kind of, well, actually even do example 3 too on that. 1, 2, and 3 on page 362. How about example 4 on page 363? And click on the self-tutor. Help explain a few more of the steps. And then just take a quick perusal through questions 1 through 7, page 363 to 364. And that will give you a bit of an idea of what we're going to be facing tomorrow in class. Of course, as always, we'll have time in class to work on this. So thanks for watching, and we'll see you in class.